Hello everyone, welcome to the course on electromagnetic theory and interference. Uh, in this fifth module, we are going to see about a transmission line calculator and impedance matching. And today's session, let's get started with what meaning of impedance matching, why it is required, and what are the types. So let's get started. Matching is nothing but designing the source and load impedance so that maximum power transfer can happen between source and load, or there can be minimum signal reflection from the load side. Why the impedance matching is very much required? Because impedance mismatch, if there is a mismatch in the impedance between the source and load, it will lead to signal reflection, or it may reduce the efficiency of power transfer. uh, these signal reflections are occurring, this signal reflection will cause a destructive interference, okay, leading to the peaks and valleys in the voltage, that is Vmax and Vmin. Standing waves will be created. So impedance matching is very much important to obtain the desirable VSWR. Our desirable VSWR is the minimum value should be 1. Max it can go to infinity, we know that. So theoretically, we are saying that VSWR equal to 1. So we have to maintain that VSWR is a measurement of telling how much impedance mismatch is there between the load impedance and the characteristic impedance, right? So we are going to use the matching network in the source and load impedances. Okay, these matching networks, component values and all can be found by using computer simulations, or by means of manual computations, or by means of the graphical tool called Smith chart that we will see in the upcoming sessions. So there are various types of impedance matching devices available. The first one is quarter wavelength line, or we can say it is called quarter wave transformer. And the second type is a signal stub matching device. And the third one is double stub matching. The first two we will see in detail as per part of this course. Okay. What do you mean quarter wave transformer? In the last year module itself, we have seen um, uh, line is having a characteristic impedance, is that not, with the length of the transmission line is lambda by 4. Okay, the input impedance of this quarter wave transmission line is going to be Z naught square by ZL. Or I can say another way, characteristic impedance of quarter wave transformer is equal to root of the input impedance into load impedance. So whenever there is a mismatch in the load and characteristic impedance, okay, when Z0 is not equal to ZL, we tell it as there is a mismatch is available and the reflected wave is existing. So for maximum power transfer to happen, this load must be, ZL should be matched to the characteristic impedance of the transmission line, so that the reflection will not be there. That is, reflection coefficient will be 0 and corresponding VSWR will be 1. So how we are going to achieve impedance matching using this particular quarter wavelength transmission line? So now let us see in the next this page. So see here, we are connecting a mismatch. One mismatch load is available, right? So this load is matched the line with the characteristic impedance, is that not, by using a quarter wavelength transmission line. Just having a characteristic impedance, is that not dash. So how to compute the characteristic impedance of this particular transmission line, QWT line? Is the root of the impedance and load. The input impedance here is nothing but the characteristic impedance of the line. Okay, and here we should note that all the impedances are real. Okay, then only the quarter wave transformer can do the matching. For example, if the load is 120 ohm, the line has 75 ohm impedance. The quarter wave transformer should have the impedance of root of input is 75 into load is 120, the square root of this value, that is around 95 ohm. Transformer should have this impedance, characteristic impedance. The same 94 ohm QWT quarter wave transformer will help us to match 75 ohm load to 120 ohm line also. Okay, we can see in this slide that before introduction of the quarter wave transformer, prior to the load, there is voltage standing waves are created. After incorporating the standing wave, to the left of this transmission line is nullified, or it is eliminated. Okay, there is no standing wave available. So the major disadvantage of this quarter wave transformer is it is a narrow band device or a frequency sensitive device. As we can see in this uh, picture, that the voltage standing wave pattern is eliminated only until certain frequency range, right? Until a particular distance only it is eliminated. After eliminated, and it will get repeated. Okay, it's a narrow band device or a frequency sensitive device. So to achieve matching over a wide range of frequencies, I have to go to the single step matching technique only. And one more thing, quarter wave transformer is able to match only the real impedance. If all are real only, it will match. The load impedance should be real, characteristic impedance also should be real. So that is a major drawback. If there is a complex load, or if I want to go for wideband matching, I should prefer single matching technique only. That we will see in the next session. So there is one worked out problem is given. So the transmission line is going to match 300 ohm. This is a load impedance to a 50 ohm line impedance. So they are asking to design a transmission line segment. So that's a quarter wave transformer characteristic impedance you have to find. That is equal to root of input impedance is 50, load is 300. So root of 300 into 50 is 122.5 ohms. So now let us see how a single step tuner can be helpful in matching. We already saw that the major drawback in using a quarter wave transformer, okay, that can be eliminated by use of this single stub tuner. Generally, stub is nothing but a small piece of transmission line, okay, which is connected in series or parallel along with this main line. Main line has a characteristic impedance, is that not right? The stub also we are going to connect it along the main line. Here it is connected in a parallel manner. Okay, this stub they are calling as tuner. This tuner can be a open circuit or short circuited section of transmission line. Here we are considering shorted stub. We have to connect this stub at a particular distance from the load, okay, from the load, and at a particular length we have to use this stub, not of any length. So here the stub also has the same characteristic impedance as a main line. Okay, here why we are not preferring the series stub means because theoretically it is feasible. Practically we have to cut this line and we have to connect, right? But a shunted stub is not in that way. We can connect easily. And one more thing, why the open circuited stubs are not preferred means because they will radiate the energy at high frequencies. So obviously, short circuited parallel stub only we are preferring, not series or open circuit stub. So the idea behind is when first it is a parallel connection, right? So it is easy to work with the admittance. So the input admittance, as we see from here, after um, placing the stub at a particular distance from the load, we can see that the input admittance is going to be 1 plus JB. This is susceptance. So after connecting the stub of a particular length, what happens? The stub is going to, stub admittance is going to cancel this susceptance by providing the negative opposite susceptance. So totally my input admittance is going to be a 1 only. Okay, in this way we are going to make ZL equal to Z0. Matching is happening. So instead of single stub connected, if you use two such stubs, okay, at a different length from the load, okay, that arrangement is called double stub matching. That also used for adjustment of load impedance. I hope you understood why we started in impedance matching, and what are the various ways in which impedance matching devices can be designed, and why there is a transition from quarter wavelength transformer technique to the single step matching and the double step. We will meet in the upcoming session. Thank you everyone. Happy learning.